Let's see. Are you going to verbalize stuff today, or did you send me?
Yes.
Okay. What do we got today?
At least I think I can verbalize some stuff.
Okay.
I'm actually going to plug in headphones real fast. Okay. Alright, so the question is solve each system algebraically for x and y, then verify your answer by graphing on your calculator.
Okay.
Which we don't have to do the graphing on your calculator part.
Okay.
But it's y equals 2x plus 3. And then underneath that, it's y equals 2x squared minus 2x plus 5.
Now, one thing that's not always readily apparent here is how to go about solving this. Because both equations are in terms of y. Well, y is the same as y, so you always set that equal to that.
Okay.
So you got 2x squared minus 2x plus 5 equals 2x plus 3. Solve that.
Do I just combine those?
Yep. In other words, whenever you have a quadratic and you have an x squared, an x, and a number, then the way you're going to solve that quadratic is by putting everything on one side and 0 on the other.
Okay.
Yeah, I put everything on the right to the left, and that gives me...
Would it be 2x squared minus x minus
4x?
Oh, sorry. I subtracted the... Okay. Right. And then plus 2.
Right. Now what's the next step?
I guess you could factor that.
There's one step that you want to take before trying to factor that.
Oh, you can divide everything by 2.
Yeah, in other words, you can find a greatest common factor. And that helps tremendously because it turns it into a first degree quadratic instead of a second degree quadratic. Now, I can just get rid of that 2. In other words, I can divide both sides by 2.
Yeah.
So now I have a very simple quadratic, which factors how?
So that'll factor to be x plus 2, x plus 1, and then x minus 1? No,
I see why you're struggling with this. I just wish I could get my students to use my method of factoring rather than this method they teach you in the schools.
Yeah.
In other words, my method of factoring is the following. Split apart the x's. That's step 1. Step 2 is figure out both signs. And that's the step that all my students want to skip. They always want to skip that part, and they want to jump straight to the answer. And notice how hard it is to jump straight to the answer.
Yeah.
You couldn't do it. But what are both signs?
Like, what do you mean?
Well, there's only one way to produce a plus 1.
Oh, well, 0 and a 1.
When you FOIL 2 linear terms together, the constant is always the result of multiplying this term by that term. In other words, the 2 terms on the right. So what do both signs have to be? The same or opposite?
Yeah.
They have to be the same. Are they plus plus or minus minus?
Minus minus.
Yeah. In other words, they have to be the same, and whenever they have to be the same, look to the sign of the middle term. So that's step 2. And once you do step 2, you can't get it wrong because there's only those are the only factors of 1.
Yeah.
And notice that that is correct. That gives me a minus 1x there and a minus 1x there. Add those two together, you get minus 2x. That's the correct middle term. That's the correct answer. That second step where you determine both signs is huge. I would love to see you do it that way every single time in 3 steps, or sometimes 4 steps. Let's see, somehow that plus sign got changed to a minus. There we go. So what's the solution?
X equals 1.
All right. What next?
Well, don't we have to plug that in for X and find Y?
Yes. They said check it. Okay. So let's go up here and, ooh. So where do we check it? I guess I could go back to the original 2 equations.
Well, we don't have to check it. It just says to solve for X and Y. So that's why I was like...
Okay, so what's Y? If X is 1, what's Y?
5.
Okay. So Y equals 5, and it better be equal to 5 in both cases. Well, this is 2 minus 2 plus 5, so that Y is equal to 5 also.
All right.
Probably is a good idea to check both. If you check both and they're not equal to the same number, then you've made a mistake, and it's a good alert that you've made a math error. Okay, and then they said also graph, right?
Mm-hmm. Okay. Oh, no.
Well, let's talk.
They said you can verify it by graphing it.
Right. I'm not gonna have you graph it on your calculator, but I know what the first equation looks like. It goes through 3, has a slope of 2. I know what the second equation looks like, kinda. It's a quadratic that opens up, but it must only have one solution. It's a quadratic that looks something like that, and that is x equal 1. In other words, that point is 1, 5, where they intersect. And in this case, they're only going to intersect in one spot. In other words, when we solve this thing, typically we would get 2 solutions, but in this case, we only got 1. Notice that with a lot of, if I plot a quadratic with a straight line, a lot of times I'll get 2 solutions, there and there. And typically I'm going to get 2 solutions. So it's a little strange, not strange, I shouldn't say strange, but it's a little unusual to only get 1 solution. And there's a variety of ways you could get 1 solution. That would give you 1 solution, or a line like that would only give you 1 solution, where this straight line on the left here never intersects with that part of the parabola. So 1 solution is fine. You don't have to have 2 solutions when you have a straight line and a parabola. What else you got?
Okay. Well, it's the same thing, just different numbers.
Okay.
But, oh, this one was actually really hard for me. It was hard for me to figure out. But x squared plus y squared equals 9. And then x plus y equals -3.
-3?
Yes.
All right. First of all, that is the equation of a circle, right? You recognize that?
No.
Well,
wait, which one is?
The top one. Whenever you have x squared plus y squared equals a number, this number is the radius squared. So that's a circle at the origin with a radius of 3. Okay? This second equation is a linear equation. In other words, if I move the x over, I get y equal minus x minus 3. It's just a straight line. Whoops, with a negative slope. Okay, so I know it's going to look something like that. So I want to find its points of intersection. Well, I can kind of do this by substitution. In other words, this is a little harder to do by elimination. Even though both appear to be in standard format, I'm going to have a hard time eliminating a variable, right?
Okay, right.
But what if I take the second equation and solve for either x or y, substitute it into the first equation, and then I'll have an equation in one variable only.
Yeah, that
Let's
seems
solve
like it
the
would work.
second one for y. So
Okay.
minus x minus 3. Now I go back into the first equation, and wherever I see y, I'm going to substitute minus x minus 3. Okay?
Okay.
Now, we've got to expand that. So what is minus x minus 3 times minus x minus 3? Just FOIL it.
Okay. So that'll be x squared plus 3x and then plus 3x again and oh wait, what did I do? And then
The last step of FOIL is that.
oh, that'll be plus 9.
Okay, so that's x squared plus 6x plus 9. So now I substitute that. So I got x squared plus x squared plus 6x plus 9 equals 9. Now what?
Could I say 2x squared plus 6x plus 9?
Yeah, always do the easiest things first. I can see a plus 9 on the left side and a plus 9 on the right side.
So I could just cancel those out.
And it's important to know that what's left here is 0, not 1. In other words, the way I canceled those out was I subtracted 9 from both sides. So now, and then you can combine the x's. So I got 2x squared plus 6x equals 0. Now, this is a quadratic that's a little easier to solve than a typical quadratic, mainly because you can factor a greatest common factor out. In other words, I don't have to factor it like I would if there was a constant. I can factor it using greatest common factor, which is what?
2.
2x.
Oh.
When you're looking for greatest common factor, always make sure you check numbers and variables.
Okay.
What's left?
So it'll be 2x plus...
If I write 2x there,
it'll just be
the
x.
step should be to multiply that by that and make sure you didn't change it.
Okay, it'll just be 3 or plus 3x.
It's just x.
Ooh.
In other words, x plus 3. But notice what I did. You don't do these all at once. You do them one at a time. I did that step first, and then I multiplied those two together to make sure that I had what I started with.
Right.
Okay, and I'm going to do the same thing to that. I'm going to multiply 2x times 3 to make sure I got 6x. In other words, when you're doing this kind of math, always be checking, especially when you're merely manipulating an equation and you're not changing it. In other words, I'm not changing this equation when I take a greatest common factor out. All I'm doing is changing, I'm manipulating it. But when I get done, that better be equal to that. That's the key. Now, what's my answer?
So I don't know. That's what I was confused about in this problem.
When you have one thing multiplied by another thing, and the product is 0, which is the case here, then either thing can be 0. So the very next step is to say, well, 2x equals 0 or x plus 3 equals 0. This part gives you x equals 0. This part gives you x equal minus 3. Those are your two solutions. And you would expect two solutions. In other words, whenever you have a quadratic, you always expect two solutions. It's rare when you don't get two solutions.
Yeah.
Remember, I mean, the last problem we had only had one solution, but it had a multiplicity of 2. In other words, we actually did have two solutions on the previous problem. It's just that both solutions were the same. Well, here's my circle, and I've got solutions. Let's see, the other part was x plus y equal negative 3. Well, that's a line like this. In other words, there's the x, the y-intercept. It's got a slope of negative 1. And notice now what my two solutions are. X equals 0 and x equal minus 3. There's the minus 3 part. In other words, there's the minus 3 x coordinate. And there is the 0 x coordinate.
Okay.
Okay? And if you plug them in to either equation, you get the y coordinate. Notice that if I plug it into this equation where x is 0, then y equals minus 3. That's that y coordinate there. And if I plug in x of minus 3, I get a y of plus 3.
All right.
And always use the easier one of the original equations to solve for the second variable. In other words, whether you're using substitution or elimination, you're always solving for one variable first. And then to solve for the second variable, you have to go back into one of your original equations, substitute your answer. Well, the easier equation is number 2, not number 1, if I'm trying to solve for the other variable. In other words, once I've solved for both x's, that will allow me to solve for both y's.
Okay.
From equation number 2.
All
right. Okay. All right. What else you got?
Let me see. Oh, okay. This says put the quadratic in vertex form and solve.
Okay.
And it's y equals x squared minus 8x plus 7.
What's vertex format? What's the general form for vertex format?
I'm not sure, but I think it's the one that's like h minus x.
It's always x minus h.
Oh, okay.
That's the general format. And this is probably the most important general format you can memorize for quadratics.
Okay.
Okay. The reason there's actually 3 formats for quadratics, but the vertex format is the key one because it immediately tells you the vertex, h and k. And with every parabola, the most important point on that parabola is the vertex. So we're always wanting to know where the vertex is. So now our job is to get that into that format. Okay? The way you do it is you complete the square.
Okay.
So when you complete the square, you're going to put parentheses around those. Leave space to complete the square and put your plus 7 out there. Again, make sure you do not change anything going from one format to the other. In other words, I'm not changing the equation, I'm just manipulating. Right?
Mm-hmm.
Okay, now, do you remember the completing the square process?
Well, it's b over 2 squared.
Now, when you're completing the square, what you do is you take half of the coefficient of the x term, which is 4.
Right.
You square it and add it.
Oh, yeah. Okay.
Well, now
that's the same thing as
just changed the equation, right?
Yeah.
So in order for me to balance out that 16 I just added, I got to subtract 16 from the same side of the equation.
Okay.
Okay, not the other side, but the same side. You will run into conic section problems where you have to do a lot of completing the square. So you want to know how to complete the square for sure. The whole reason you complete the square is that it allows you to write that quadratic as a linear term, x minus 4 quantity squared. Every time you complete the square, you can write the quadratic as a linear term squared.
Okay.
Okay, and then I combine those two and I get minus 9. Well, now notice that I've got it in general format. Perfect. What's A?
A is going to be...
A is 1.
Oh, because there's no... Okay.
Because there's no coefficient out.
Coefficient, right, okay.
Right. H is what?
Negative 4, or just 4, positive 4.
Positive 4. And K is what?
9.
Negative
9.
Make sure you don't get the signs wrong.
Okay.
One thing in math you cannot do is get the right answer and the wrong sign. It's just as bad as getting the wrong answer. You're going to get partial credit. If you get...
Should I put...
Go ahead.
Should I put a 1 in front of the parentheses, or does it not matter?
No, you do not need it. This is fine for an answer. What exactly did they want here? Just you to put it in vertex format?
And then also to find the solutions.
That's a bit nebulous of a question. The solutions to what?
I don't know. It just said put the quadratic in vertex form and solve.
Okay. Well, we put it in vertex form, but like any time you have one equation and two variables, you can't solve it.
Could we solve it when it was in...
No.
Oh.
No. Here's what you would do if you were to try to... When they say solve, perhaps they meant find the zeros.
Yeah, maybe.
Okay. Well, when they want you to find the x-intercept, they're saying, well, that's where y is equal to 0. So, okay, now if I want to set y equal to 0, I can solve. And that's okay. Setting y equal to 0 is what you do when you try to find the x-intercepts. Now, what's a nice, easy way to solve that? Without expanding it. In other words, I could go back to the original, this one, number 1, and factor that. It's x minus 7 times x minus 1, so I could solve it that way. But I suspect they want you to solve it once you've gotten it into vertex format.
Okay.
Okay. And this I don't actually need to factor. How can I solve this?
Well, I'm not sure, but could you, this is just a guess, but could you add 9 to the other side and then square root
Perfect.
those?
Perfect.
Okay.
So there's step 2. Now take the square root of both sides. What do you get?
It'll be 3 equals,
No?
or 3 plus or minus,
Plus or
plus or minus
minus.
3 equals x minus
Remember
4.
what I've said is that whenever you're solving an equation by taking the square root of both sides, always begin your answer with the words plus or minus.
Okay.
Okay? Now what?
So it could be x equals,
Hold on. Let's add 4 to both sides.
oh, right.
So we get that. And now that's actually 2 answers. What are they?
So you could do -3 plus 4 equals x, or +3 plus 4 equals x.
Okay.
So,
I get
so really,
7 or negative or positive 1 rather.
okay.
Okay.
Yeah, I just didn't simplify.
And notice that that's the same solution I would have gotten had I not put it into vertex format. In other words, if I factor that quadratic, I get x minus 7 times x minus 1. And that immediately gives me x equals 7, x equals 1. So it would clearly have been a lot faster to factor it. But the whole point of this exercise is learning how to complete the square.
Okay.
Okay, completing the square is, there's a lot of places in algebra where you have to complete the square. Do we have another one like that? If we do, I won't erase that vertex format.
Yes, we do.
Okay.
And it is y equals 3x minus 12x plus 27.
3x squared
Or, yeah, 3x squared.
plus 27?
Yes.
Okay. So we got to put that in this format. Well, the one thing about completing the square, first of all, you always isolate those two with parentheses. You cannot complete the square until the coefficient of the x squared is 1. So what do I have to do first? Factor out of 3.
Oh, right, because they all, okay.
Now that leaves us with this. I'm going to leave room to complete the square. Now, is that exactly the same as what I started with?
No.
Yeah, it is. Distribute the 3, and you get 3x squared minus 12x. Add 27. That's exactly what I started with.
Don't you have to divide the 27?
No? Remember, everything's on the same side of the equation here.
Okay.
All I did was factor out a 3 from the x squared and the x. I didn't factor out a 3 from the 27, purposefully. I want to, first of all, there's something really important to be demonstrated here. Okay, now let's complete the square inside the parentheses. How do I complete the square again?
By taking the b value, dividing it by 2, and squaring it.
Which gives you what? It's always a plus, incidentally.
It'll be 16.
No, you take half of the b value.
Oh, right, so it'll be 4.
Okay. How much did I just add to the right side of the equation when I wrote that 4 in there?
You added 4.
Actually, I added 12. That 4 is being multiplied by
because of the 3.
Yeah. So I really added 12, which means I have to subtract 12.
Huh. Okay.
Okay. So whenever you have to factor out that coefficient from the first term, which we did, make sure that when you balance the side of the equation that you multiply that 3 by whatever you wrote in there. And now notice what I'm going to have. That's going to turn into x minus 2. It's always what you got when you took half of that, quantity squared, plus 15. Now I have it into perfect vertex format. And A is 3. The vertex is where?
The vertex will be 215. Good.
Now let's solve it. Now, the one advantage in having it in vertex format is it actually makes it rather easy to solve for your zeros. We don't have to factor or anything. If we'd have started from the beginning, I'd have to factor. But what I can do here is move this 15. In other words, I start by doing this, setting y equal to 0. Solve this. There's two ways to solve this. You can expand this out, multiply it by 3, combine it with the 15, and you're back to the starting spot. In other words, we're back to our original equation. So there's an easier way to do it. In other words, if we get back to our original equation, then we have to figure out how to factor that, right?
Right. I was just going to subtract 15.
That's the way to do it. In other words, once you're in vertex format, you can always solve them that way. In other words, subtract 15. Divide by 3. Now what?
Square root both sides.
What's the square root of negative 5?
I don't really know.
No solution. You cannot take the square root of a negative number.
So, right. Well, I mean, unless you make it imaginary, right?
Well, okay. Have you had imaginary numbers?
Yes.
Well, then let's do the imaginary solution. I wasn't sure if you'd had it. So if you take the square root of both sides, what's the left side give you?
X minus 2. Oh, the left side? Okay, let me figure this out. Would it just be negative 5i? Or plus or minus?
Well, it's... Here, let's break it down as to how to do this, because this is not that obvious. When I'm looking at the square root of negative 5, first thing I'm going to do is turn it into the square root of 5 times the square root of negative 1, right?
Okay.
That's equal to square root of 5 times I. And it's plus or minus because whenever you take the square root of both sides in an equation, the first words out of your mouth need to be plus or minus. So it's plus or minus root 5 times I. The I is not under the radical sign. Let's erase all of this. Now I still got that 2 over there. So let's bring the 2 over. And that gives me this. And notice that looks an awful lot like what you would get if you use the quadratic formula.
Yeah.
And that's on purpose. In other words, that is correct. If I go back to the original equation and somebody says solve this, in other words, set it equal to 0 and solve it, well, I would use the quadratic formula. And after using the quadratic formula, I would get this as my 2 answers. with me?
Yep.
Okay. It's no solution only if you haven't had imaginary numbers.
Okay.
But
otherwise I can solve?
Not that, if I said, what's the domain? No, the domain is all real numbers. But if I said, what's the range is no range, no solution.
Okay.
Okay. In other words, here, let me be a little clearer here. If I said, what's the domain of that? It's positive numbers only. X has to be greater than or equal to 0. I don't even count negative numbers in the domain, because when you're talking domain and range, there's no such thing as imaginary numbers. In other words, I do not consider the existence of imaginary numbers to figure out what x can be in square root of x. It has to be positive. You cannot take the square root of negative numbers. Imaginary numbers are an invention of mathematics to help you do higher mathematics. So they're not really real, although some mathematicians might argue with that. Turns out that the toughest math problem in history is Riemann's hypothesis, which is still being weighed. Is
that like a formula?
Well, no, it's a hypothesis. It's difficult to explain. It's a very, very interesting hypothesis that was invented 150 years ago by Riemann, and it actually has to do with imaginary numbers. But they say that if anybody can prove his hypothesis, that it might be the secret to the entire universe. It might be the theory of everything. It might prove...
What's it called again?
Yeah, it might prove the link between quantum physics and theoretical physics, or rather Einstein physics, the physics of the large. Right now, they're still trying to get the two to balance, and they can't do it. And a lot of people think that Riemann's hypothesis is the way to do it. What Riemann's hypothesis basically says is the zeros of the zeta function line up in a straight line. And I know of at least 3 mathematicians that have been driven crazy by spending their entire life trying to prove that.
Oh, wow.
And the zeros of the zeta function have to do with imaginary numbers. It's if you did a graph with imaginary numbers in it, the zeros of that zeta function is called, would line up in a straight line, and nobody's been able to prove it. And if anybody could prove it, it would instantly be the toughest math problem ever solved, the most important math proof ever made. That's how important it is.
Oh, wow.
And
do you think someone will prove it?
Maybe another 100 years. Every 100 years at the turn of the century, they write 25 to 100 math problems that they would like to see solved in the next 100 years. Riemann's hypothesis was on the list in 1900, and they had 100 problems on there, and all but 7 of them were proven over the next 100 years. And so,
wow. So it should be solved like pretty soon.
No, not really. It remains in other words, it remained on the list for the year 2000.
Oh.
But they added 18 more, so there's 25 math problems on the list for the year 2000, and already like 8 of those have been solved. But
that's crazy.
Not Riemann's hypothesis. Did you ever see the movie called A Brilliant or Beautiful Mind with Russell Crowe?
Oh, is that the one with the janitor who's...
No, that's the one with Matt Damon, where the janitor solves that real important problem on the...
Yeah, like on the chalkboard, like while he's just like going on.
A Beautiful Mind is, boy, if you ever get a chance, watch it. It's really good. It's about the mathematician John Nash, who just recently died, but it's about his mental struggles that he went through trying to solve Riemann's hypothesis. It actually made him crazy, and they don't tell you that when they give you the movie. So when you're watching the movie, you see all these strange things happening, and they're just figments of his imagination.
Oh, wow.
He's legitimately whatever you call that condition where you're seeing things that don't exist.
Yeah.
He legitimately went nuts. And he says he recovered from that mental illness. I saw an interview with him just a few years ago when he was like 75. And he said his belief is that the attempt to prove that hypothesis is what made him go crazy.
Yeah.
And same thing happened to a couple of other mathematicians in the early 20th century. So, bet you didn't know there was a danger to trying to do hard math.
Didn't. That's crazy. Wait, so pi is definitely like unsolvable, right? Like it's infinite?
Yeah, it's irrational. There's no way you can write that as a fraction.
Okay, because someone told me that they found like an n to pi.
2 as a fraction either. I'm sorry, what were you saying? What did you say?
Oh, no, like my brother told me that like scientists are finding like an n to pi or something, or they're like coming close.
Scientists, and this kind of led to Riemann's hypothesis. It does have something to do with pi. Scientists have never found a pattern to prime numbers. If you list prime numbers, okay, there's no pattern. I can go out to 1 billion terms and you would think that they would find a pattern between prime numbers, but there's not one. They've never found one yet. If you go up this list, sometimes you can go 100 numbers between prime numbers. Sometimes you just go 2 numbers between prime numbers. And no matter how far they go, they do not find a pattern. And people think there should be a pattern. And if you can ever find the pattern in prime numbers, that might also be the solution to Riemann's hypothesis.
Oh, wow.
Yeah, so they're related. Riemann himself actually found somewhat of a pattern where, believe it or not, if you take all the prime numbers and multiply them all together, you get pi in your answer. It's not quite multiplying all the prime numbers together. It's doing some various manipulation to them first, but after the fact that pi is part of the answer is rather astounding. If you look at the sequence of prime numbers, pi has nothing to do with any of these numbers, right? I mean, pi is not even in the question. But if you, there is a relationship between prime numbers and pi, which is astounding, because pi is the circumference of a circle divided by the diameter. That's its definition. Has nothing to do with prime numbers, but it does. There is a relationship, and it's one of the most interesting relationships in mathematics, and nobody has quite figured it out yet. But
well, can't some things be like unsolvable?
Yeah. Well, yes,
like,
no.
Could
In other words, Riemann's hypothesis was worked on by 2 mathematicians for 20 years. They both had mental illness afterwards, and then they kind of came to the conclusion that they didn't think it was true. Not only could they not solve
it. Oh, yeah, because it's only a hypothesis.
Well, it's a hypothesis, exactly. We don't know if it's true or false. Riemann was very convinced that it was true. He just couldn't prove it. And that's the case with most math theorems, is that the ones that made that list of 25 toughest problems are probably, most of them are true. It's just a question of proving it. And that's the toughest part of math, is proving stuff. It's like somebody had to prove the Pythagorean Theorem. A squared plus B squared equals C squared. Well, even though every right triangle you can possibly think of is this, it applies, that still's not proof. Okay? Because you can't possibly cover all the numbers in the number line. So you can't prove every combination of numbers. But there is a way to prove this. And the proof kind of goes something like you draw a square there, which is A squared. You draw a square there, which is B squared. And then you prove that the area of A plus B is equal to that.
Yeah.
And that's how you prove the Pythagorean theorem. And that's not easy, trust me. In high school, the teacher said, okay, everybody's assignment is to prove the Pythagorean theorem. There was only one person in class that came back the next day with the proof.
Yeah.
So it's not an easy thing to do. Any of these mathematical proofs. But anyway, what else you got? We got another few minutes here.
Okay, trying to find one that... Oh, it says, write a quadratic function in any form from the given information.
Okay, good. These are hard.
And the information is vertex and parentheses -2, comma 4 through the point parentheses -1, comma 1.
All right. What's the general format in vertex format?
It will be y equals a.
You know what I would rather see rather than you turn the page in your book? I'd rather you see if you have it memorized properly. Tell me what you think it is. Starts with A.
Okay, and then x minus h plus k?
Yes.
Okay,
that is the best way to memorize stuff. If you look it up every single time, you'll never memorize.
Okay.
The way to memorize stuff is to see if your memory has it correct, write it down, and now maybe look it up to make sure that you wrote it correctly. Okay? If you do that process, it won't be long before you have it memorized. Trust me. Okay?
Okay.
So, how much can I fill in? I don't know what A is, but I do know H and K.
H will be 4, or I mean -2, so it'll actually be +2.
Correct.
And then K will be 4.
Okay. Now, I have that equation, and I need to solve for A. In other words, my final answer needs to have a number for A. Well, there's 3 variables in that. But they told me that this parabola went through that point right there. So that point has to satisfy my final equation. So I'm going to plug in the 1 for y. I'm going to leave that as A. I'm going to plug in the -1 for x. And now I can solve that for A. In other words, now I have 1 equals 1A plus 4. Now I have -3 equals A. Now I have my full equation. Y equals -3, that's what A was. X plus 2 squared plus 4. Whenever they want a final equation, they always want an X and a Y in it. That's it. In other words, you're going to solve for A, H, and K. Always.
Okay.
So it's actually, these are pretty easy when they give you the vertex, because that instantly lets you solve for H and K. They can be a little harder. The hardest problem would be if they just gave you 3 points that were on the parabola. Then that becomes rather difficult to solve. Then you end up with 3 equations and 3 unknowns.
Okay.
Okay, and you'd have to solve them as you would any system of 3 equations and 3 unknowns.
All right.
And let's just talk about that for a second. We won't do another problem because we're almost out of time here. But
okay.
Say they gave you 3 points. There's 3 points that are on our parabola.
Right.
Okay. Well, I can generate 3 equations from those 3 points, right?
Right.
Plug in the first equation. I get 1 equals a times minus 1 minus h. I no longer have a vertex, notice.
Mm-hmm.
So let's erase that vertex. And now I have a second equation that's going to come from that one. So 3 equals a times 2 minus h squared plus k. And finally, my third one is 7 equals a times 5 minus h squared plus k. Well, notice what I have. I have a system of equations, and I have the same number of equations as I have variables. My variables are a, h, and k in all 3 equations. So whenever you have the same number of variables as you have equations, you can always solve for the variables. And then I'm going to end up with a final equation where I have a number for a number for h, and a number for k. And that'll be my, plug those 3 numbers into that format, and you got your equation of that parabola.
Mm-hmm.
Okay. But obviously this is a lot harder if they give you 3 points, because solving a system of equations with 3 variables is a long process. You did it at the beginning of the year, right?
Yeah.
Didn't they give you 3 equations? It seems like that's what they start you off with in Algebra 2, is 3 equations,
Yeah.
3 variables. So you have to know how to do that. And it's hard, but it can be done. As long as you have the same number of variables as you have equations, it can be solved. If I have 5 variables and 5 equations, I can solve it. But if I have 2 variables and only 1 equation, I cannot solve it. Now, when they said solve these, they meant solve for the zeros. And when I'm solving for the zeros, I'm going to set y equal to 0 always. Because when I go to find my zeros of that parabola, those are my zeros, and they're the x-intercepts because y is equal to 0 at both of those spots. All right. Good place to stop, unless you have any last questions.
No, I think that's it.
All right. I will talk to you on Wednesday, Anna.
All right. Thank you.
All right. Bye-bye.
Bye.